So in this lesson, what we're going to look at is X-ray production as part of the nuclear detonation sequence. Now, if you'll remember back to the lesson on charged particles, if we have a light charged particle, like an electron, that's traveling through material and it gets close to a nucleus that has a lot of positive charge in it, that electron's path will be bent around that nucleus. Now, when this occurs, we have to, basically we're undergoing radial acceleration of the electron, and we're going to have to dump some extra energy that it's gained, and it does this by emitting a photon. If the electron is moving fast enough and if the nucleus bends the path enough, what we end up with is an X-ray being produced, and this is bremsstrahlung or breaking radiation. Now, there's another type of X-ray creation that we talked about, which was the characteristic X-rays, but these aren't really going to figure too much into the discussion that we're going to have here. Now, where do these electrons or the ions or nuclei, where do they even come from? Well, we have an equation that basically correlates energy to temperature, and then an even more complicated equation that correlates energy to mass, temperature, and volume, which is the one we see here on the screen. Now, if you knew everything, if you knew the volume, you knew the mass, the A and C are both constants, and you knew the yield, then you could calculate basically what is the temperature. And if we do this, for most weapons that have any kind of a yield, we find out that the temperatures in the core of the weapon get into the millions and tens of millions of degrees. So now we correlate temperature to kinetic energy. So if we're at millions of degrees, that means that all of the atoms within this material have a ton of energy. In fact, they'll have so much energy that they're going to fully ionize, that is, eject all of the electrons that they have. So now you have a plasma that has electrons that are moving around at that, at the speed of whatever that kinetic temperature is, and you have a bunch of nuclei. So naturally, the electrons, some of them are going to come near the nuclei, have their paths bent around them, and produce these X-rays. And this correlates to full ionization. So once we have the temperatures high enough, everything's ionized, we start producing X-rays simply through the motion that they gain from this temperature. Now, a different kind of temperature that comes up is kind of related just to the photons themselves. So we talked about temperature as far as kinetic temperature, which affects the kinetic energy of particles. But now the X-rays themselves, photons, can be considered to have a temperature. And this is almost exclusive to what we're talking about here with nuclear weapons. Now, there are 3 different levels of temperature, which we'll talk about here in one sec. However, before we do that, we have to at least be aware that when these electrons produce X-rays, okay, they're going to produce them in a wide distribution of energy, depending on, of course, how much kinetic energy those electrons have and how much their path is bent around a positively charged nucleus. So if we took and sampled all the different energies that we could get from these electrons that are produced by this temperature, what we would see, if we plotted them, would be a distribution like we see on the screen here, which is called the Planckian distribution. Now, this is a statistical distribution. This is just what happens. It's the way that the electrons interact with the nuclei. And what we see here is that we can go from 0 energy or very, very low energy in the case of electrons not having too much kinetic energy and being far away from nuclei. We have an average energy of about 3, or a peak energy of about 3 keV. Average energy is probably closer to 4 keV, but we can go all the way to the upper end to 10 to 15 keV, although the probability of that occurring is very rare. So now we have all of these X-rays produced by our electrons, and they have a wide range of energy that fit into this distribution. So where does the temperature come in? Well, there's hot and cold. That's it. No real temperature, just sort of a descriptor. And there is a very defined dividing point between them. And cold X-rays have energies of less than 2 keV, while so-called hot X-rays are going to be above this value. So once we've got these X-rays being produced within this, plasma now, fully ionized material, why don't they just escape the bomb casing, right? They're photons, they're energetic photons, so they should be able to, just get out and radiate away, in which case all the energy that we've been collecting through the fission process for our weapon should just be dispersed and we really shouldn't get an explosion. Well, the long and the short of it is, all the stuff that's inside the bomb, to include its casing, okay, is going to interact with these X-rays on their way sort of out of the bomb. And they're not going to make it for quite some time, relatively speaking. So these X-rays are going to interact with things like the heavy metal of the bomb casing, the heavy metals that are possibly in the circuitry, and all the other stuff crammed inside. So what ends up happening is you produce these X-rays, they start flying around, and then they start interacting with the material inside the casing. They get absorbed by atoms in the material. Now those atoms are in a very excited state. Those atoms then start to eject their electrons at some energy, and now they're ionized. Now you have more energetic electrons, which are then going to interact with other nuclei that are there, producing more X-rays. Okay? So imagine this, if we start with a core, and the X-rays are produced here, and as the X-rays start to move away from the core, they start interacting with the material right next to it. So they'll go in, they'll ionize, they'll be absorbed, they'll re-radiate as those electrons interact with other nuclei, and now we have more X-rays. And then the process repeats. We move to the next layer that's directly against our plasma. X-rays get absorbed, electrons get ejected. Those electrons then produce more X-rays as they fully ionize that material. And so on, and so on, and so on. So little tiny microscopic layers are in very rapid succession ionized, where the X-rays that came before are absorbed and then re-radiated as the ejected electrons interact with, again, nuclei to create another wave of X-rays. Every time this happens, your X-rays lose energy. Okay, that transition between being absorbed into ejecting the electrons from whatever atom absorbed them, it takes a little energy each time. So what ends up happening is the average energy of your X-rays starts to decrease. Now, the more material that's inside there that your X-rays have to interact with in order to be re-radiated, the lower that temperature will go. So the end point to this is when you fully ionize the casing of the weapon, right? So now there's literally nothing holding all of this energy back, and that's the point where you get a nice bright flash, and the first bright flash, and the weapon detonates. Okay, and this is all because those X-rays, which carry about 80% of all the energy that we've produced via those fission reactions, okay, 80% of that is moving outward from the core very, very quickly, and then breach the bomb casing or the weapon casing into the atmosphere. And we're going to talk about what happens when we start talking about like shock and blast effects. What happens when those X-rays, leave the casing and start interacting with the atmosphere or the environment. So that's how we get X-rays, and basically that's what they do. So if we have extremely thick casings or weapons with a lot of stuff in the middle, we're going to see a bit of a different response than if we had something that was very streamlined, very little inside, and a very thin casing. Okay, old weapon designs had super thick, like iron or steel casing. They had a ton of explosives in there, especially with regards to an implosion type weapon. There were wires and detonators and just a whole bunch of stuff. So those older weapons, generally speaking, because they had to absorb and re-radiate those X-rays a whole lot of times before they finally completely ionized and vaporized the case, they will have lost, on average, a lot more energy than like a newer weapon. And this results in the X-rays, on average, being considered cold, or less than 2 keV. Modern weapon designs, because of space requirements or constraints, or weight requirements or constraints, being put on something like a ballistic missile or a smaller aircraft than the largest bombers in the fleet. The weapon designs evolved to be much more efficient and need a lot less componentry, and the weight goes down and the amount of material goes down. So newer weapons tend to radiate hot X-rays as opposed to the cold ones that we would see with the older weapons. Now, so don't fat shame a nuclear weapon. It's just not going to be happy, and yeah, the results are probably going to be suboptimal. So what does it all mean? Well, X-rays end up, when they interact with the atmosphere, as we'll discuss later, they generate like all of the blast and shock. They all start with these X-rays that are escaping the weapon. Now, if we have the same volume, more mass, which I just explained, we get colder X-rays than we do with less volume, less mass, less stuff for those X-rays to have to go through before they finally escape. Now, at lower energies, for photons in general, the photoelectric effect is quite dominant. And this is how we get that absorption and re-radiation of these X-rays as they move outward from the fissile material core of your weapon. So the photoelectric effect is just basically, if we see here, for something like carbon, at below 2 keV, I mean, that's all there is. That's all that interacts. It's all by photoelectric absorption. Okay, so this energy would be completely absorbed and then re-radiated as it ejected electrons and so on and so forth. Now, when we get into the higher keVs, we see Compton scattering starts to come up, but it's still mostly dominated by photoelectric absorption. So this is how we absorb and re-radiate X-rays. But it's also something else that's important about this, and that is, if you think about it in the atmosphere, right? And we have our X-rays being produced and re-radiated or whatever until they finally breach the case of the weapon. The difference between, say, 3 keV X-rays and 2 keV X-rays isn't going to be much, because they're all going to interact with the atmosphere in approximately the same way. You'll see slight variations, but nothing major. However, if we talk about a weapon detonation in space, where there are things that can be interacted with by the X-rays, like, I don't know, satellites, re-entry vehicles, shuttles, basically anything out in space, if we have colder X-rays, because of the tendency to interact by photoelectric effect, the lower energy you have, these lower energy or colder X-rays can deposit, or will be more likely to deposit, large amounts of energy in something like a satellite or a re-entry vehicle, and doing quite a bit of damage, more so than would be created if the photon energies was much higher. So that's pretty much the only main difference that we are concerned with right here, is between cold and hot X-rays. Is first, you should know the difference, and then why you get cold versus hot X-rays. And lastly, that cold X-rays are much worse for something in an exoatmospheric or space detonation, for anything that may be anywhere near them, right? Again, satellites, shuttles, re-entry vehicles, etc. So that's pretty much it for X-rays. I mean, most of the information that we need to understand what's going on, we covered previously in photon interactions and also charged particle interactions. But in this lesson, we just sort of pull it all together and see that X-rays are produced because of the heat that's generated through the fission chain reaction. These X-rays then basically are absorbed and re-emitted or re-radiated as the ionization continues throughout the inside of a weapon until it breaches the case, in which case they interact with the atmosphere, and we get to talk about that a little bit later on. So that's pretty much all I have for you. We'll see you next time.